A moving charge in a magnetic field 1. The figure at right shows a uniform magnetic field of magnitude B that points entirely in the y direction. Entering the field is a charge of magnitude Q moving at a velocity v, which is directed at an angle theta relative to the x direction. We see that this is a positive charge here. Below the original figure is another, that's this one, which shows an enlarged velocity vector. On this, draw the x and y components of the charge's velocity. We're going to have a y component, we'll call it Vy, that goes there, and then we have an x component that looks kind of like that. Which velocity component is unaffected by the magnetic field? If we look at the figure at the top, you can see the magnetic field is directed towards the top of the page. And we recall the equation for the magnetic force on a charge that is moving through an external magnetic field. You see it's a cross product. The Vy component is not going to be affected at all by the magnetic field. It's not going to be changed at all. Which velocity component is affected? Vx is going to be affected, but only in the sense that it won't be pointing in the x direction anymore. It will be pointing in a slightly different direction. What we'll find out here in just a second is that the speed will not be changed. The direction will. So this Vx vector in very short order will not be pointing entirely in the Vx direction. It will be pointing maybe a little bit more towards us or a little bit away from us, which I think we'll find out in the next question. In what direction will the magnetic force on the charge point? We'll want to use our pat-pat right-hand rule and recall that the way we do that is we put our thumb in the direction of the velocity, and in this case we're just going to worry about the velocity in the x direction because we've just mentioned that Vy is not affected due to this magnetic field. Right thumb points in the Vx direction, magnetic field lines point to the top of the page, out of the page, towards us by the pat-pat right-hand rule. What will happen to the charge's speed as a result of that magnetic force? And we alluded to this just a second ago, and here it is in words. V remains constant because this magnetic force is neither parallel nor anti-parallel to an existing component of V. If the Fb were parallel to an existing component, then the speed would increase. If it were anti-parallel, the speed would decrease. You should have learned in mechanics that if you have a velocity vector pointed that way, let's say, and if you have an acceleration vector, let's say that's pointed like so, this acceleration vector can be broken into a tangential component, I'll call that AT, as well as a centripetal component, AC. The tangential component will cause the speed to increase. The centripetal component will cause the direction to change in this case. And what we have with magnetic forces always, and this is what's coming here in point F. There is an extremely important point here, which is that a magnetic force on a moving charge cannot cause the charge to speed up or slow down. It can only serve to change direction of the velocity of the particle. Consider this diagram here. Determine the magnitude of the magnetic force on the charge. We've gone through that the cross product equation looks like that, which means that the magnitude of Fb is given by QVB, and then let's see, which is it? Is it sine or is it cosine of theta? And the way I remember is that this is called the cross product, which has a C in it as a starting letter. And the trig function that goes with that is not the one that starts with a C. That means it's going to be sine. Cross product, we use the sine. The scalar product, or the dot product, is involving the trig function that doesn't start with an S. That's the way Mr. Bergman remembers, is it sine or cosine? The trick here is, though, that this theta is when the vector tails are together. And you can see right here that this angle is not the angle that is formed when the tails are put together. See, if I mentally move one of these magnetic field lines and I direct it right here, what's the angle when the tails are tied together? It's 30. So that number right here, in order for us to calculate this, we're going to want 30. I'm going to put a couple of exclamation points by there, because that theta is when the tails are together. What we're going to do here is we're going to say the charges are in coulombs, the charge is in coulombs, the velocity is in meters per second, the magnetic field is in Teslas. Those are all the correct unit. So I'm going to be a little bit lazy and I'm just going to leave them off when I show my work. But of course, whenever we hit equals, we always want to put a unit. Q is 3, V is 6, B is 8, and then we want the sine of 30, not the sine of 60. Even though 60 is what's shown in this picture, in that equation, it's when the tails of the vectors are tied together. We want the angle between those. So that's going to be 1/2, and that's 8. So that's 4 times 18, which is what? 72? 72 newtons. That's the magnitude of the force. What's the initial direction of this force? The y component is unaffected, but the x component of the velocity is going that way. This is a positive charge group towards us. How far in the y direction will the charge have traveled 5 seconds after it enters the B field? Remember, Vy is unaffected, either in magnitude or direction. The distance in the y direction is going to be Vy, which is what? 6 times the sine of 60. That's Vy, multiplied by the time, and that's 5 seconds. Now the sine of 60, that is √3/2, so you'd have to maybe use a calculator to figure that out, and when I did that, I got about 26 meters. Lastly, describe the trajectory of this charge assuming the uniform B field goes on for a while. This charge is going to travel in a corkscrew path. Vy is going to be entirely unaffected in either direction or magnitude. Vx, what started out as Vx, it won't increase or decrease, but the direction will constantly be changing. And so this charge will be traveling in a corkscrew path.